What if the most fundamental truth you believe about reality, about the very fabric of space and time, were simply not the whole story? We look up at the night sky and see a comforting tapestry of stars, a predictable clockwork of planets, but hidden within that darkness are secrets so profound they challenge our very place in the cosmos. At the heart of this mystery lies one of the most awe-inspiring and terrifying phenomena in existence, the black hole. These are not merely cosmic vacuum cleaners or distant points of no return. They are the universe's ultimate paradoxes, regions where the laws of physics as we know them break down completely. To even begin to understand a black hole is to take a journey to the very edge of human comprehension, and what we find there will change you. It will reshape how you see the night, the stars, and your own fleeting moment in this vast, astonishing universe. This video is that journey. We are going to explore 30 facts about black holes that are so incredible, so mind-bending, they feel more like science fiction than science. But every single one is grounded in the cutting edge of astrophysics, in the work of brilliant minds who stare into the abyss and dare to ask the biggest questions. We will uncover how a black hole can stretch you into a strand of spaghetti while simultaneously crushing you into a point smaller than an atom. We will investigate how they might be gateways to other universes, or perhaps cosmic prisons containing the remnants of entire civilizations. We will see how they warp time itself, creating scenarios where minutes for one observer could be millennia for another. This is not just a list of trivia, this is an expedition into the unknown, and you have a front row seat. So prepare to have your mind expanded. Forget everything you think you know about gravity, about matter, about the nature of existence. Over the next while, we are going to peel back the layers of reality and look directly into the heart of darkness. We will start with the fundamental yet utterly bizarre principles that give black holes their power, and then voyage outward to explore their incredible influence on the galaxies around them and the profound philosophical questions they raise about our universe. By the end, the silent, starry sky will seem anything but silent. It will be a roaring, dynamic, and deeply mysterious arena where the most extreme events in creation are playing out. Let's begin. The name itself is a kind of cosmic misdirection, suggesting an empty void, a simple hole in the fabric of space. But the reality is infinitely more strange and far more terrifying. A black hole is not an absence of something, it is an extreme concentration of everything. Picture, if you will, a star far more massive than our own sun. For millions of years, it burns brilliantly, its outward pressure from nuclear fusion perfectly balancing the immense inward crush of its own gravity. But when such a star exhausts its nuclear fuel, that delicate balance shatters. In a cataclysmic instant, there is nothing left to push back against gravity's relentless pull. The star's own immense weight causes it to collapse inward at a significant fraction of the speed of light. The entire mass of that gigantic star, which once spanned millions of miles, is crushed into a single point of infinite density, a concept so baffling physicists call it a singularity. This is the true heart of a black hole. Surrounding this incomprehensible singularity is the boundary that truly defines a black hole, the event horizon. Think of this not as a solid surface you could bump into, like the shell of an egg, but as a point of no return in the very geometry of spacetime. It is an invisible sphere, a threshold where the gravitational pull becomes so intense that the escape velocity exceeds the speed of light. Since nothing in our universe can travel faster than light, anything that crosses this boundary, be it a spacecraft, a planet, or a particle of light itself, is irrevocably lost to our universe. It's like a cosmic waterfall. You can paddle safely in the river upstream, but once you cross the edge where the water plummets downward, there is no paddling back up. The current is just too strong. From our perspective outside the event horizon, we would never actually see an object fall in. As it approaches this boundary, time would appear to slow down for it until it seems to freeze, fading from view as its light is stretched into invisible wavelength. So, a black hole is the opposite of a hole. It is one of the most massive, densest objects conceivable, a gravitational monster born from the death of a giant star, cloaked by the ultimate one-way door of the event horizon. And yet, for all their immense power, the very existence of these cosmic giants hinges on a set of ideas so revolutionary that even their originators struggled to accept where they led. It's a story that begins not with a telescope but with a pen and paper. In 1915, Albert Einstein presented his masterpiece, the theory of general relativity, which proposed a radical new idea. Gravity is not a mysterious force pulling objects together, but rather a curvature, a warping, of the very fabric of space and time caused by mass and energy. Picture the universe as a vast, stretchy rubber sheet. Place a heavy object like a sun on that sheet, and it creates a deep well. Planets orbit not because they are being pulled by an invisible string, but because they are simply following the curved geometry of that well, like a marble rolling around a funnel. This was a breathtaking leap in our understanding of the cosmos. Just months after Einstein published his equations, a German physicist and astronomer named Karl Schwarzschild, while serving on the brutal front lines of World War I, managed to find the first exact solution to them. He was calculating how space-time would be curved by a perfectly spherical, non-rotating mass. What he discovered within the math was astonishing. His solution indicated that if you compressed any amount of mass into a sufficiently small, critical radius, now called the Schwarzschild radius, the curvature of space-time would become infinite. The rubber sheet would be stretched into an infinitely deep pit, a point where the mathematics simply broke down. He had, in essence, discovered the event horizon, the fundamental blueprint for a black hole, purely from the mathematics of relativity. The profound irony here is that Einstein himself was deeply skeptical. To him, Schwarzschild's solution was a fascinating mathematical abstraction, a theoretical Chinese letter case that could not possibly correspond to a real physical object in the universe. He believed that some natural process, some unknown mechanism, would always prevent matter from collapsing to such an extreme state. The idea of a singularity, a point of infinite density, seemed physically unreasonable, an artifact of the math rather than a description of reality. So, while Einstein's theory provided the very keys to understanding black holes, the great physicist himself considered them too strange, too monstrous, to be anything more than ghosts in the machine of his equations. It would take decades of further theoretical work and eventually powerful astronomical observations to prove that these mathematical curiosities were not only possible, but were, in fact, some of the most common and influential objects in the entire universe. Yet for decades, these theoretical monsters remained just that, theoretical. A stunning prediction on paper with no proof they actually existed in the cold, dark expanse of space. How do you find something that, by its very nature, emits no light and hides behind an absolute veil? The answer came not from looking for darkness, but from listening to the screams of dying starlight. The hunt culminated in 1971 with an object known as Cygnus X-1, a discovery that turned a mathematical curiosity into an observed reality. The story begins not with optical telescopes, but with instruments that see the universe in a much more violent light, X-rays. Earth's atmosphere blocks this high-energy radiation, so to detect it, scientists had to send instruments above the blanket of air. In the 1960s, rockets and early satellites equipped with X-ray detectors began to scan the heavens, and they found something astonishing. The sky, which appears so serene to our eyes, was crackling with intense, powerful sources of X-rays. One of the brightest and most persistent of these sources was in the constellation Cygnus, dubbed Cygnus X-1. This was the clue, but it wasn't yet the proof. To solve the mystery, astronomers turned their traditional telescopes toward the spot in the sky where the X-rays were emanating. What they found was a brilliant blue supergiant star, a behemoth known as HDE 226,868. But this star was behaving strangely. It was wobbling as if it were locked in a tight, frantic dance with an unseen partner. By carefully measuring the star's motion, they could calculate the mass of its invisible companion. The result was staggering. The unseen object had to be at least 8 or 9 times more massive than our own Sun. And there was the problem. According to the known laws of physics, an object that massive could only be one of 3 things: a white dwarf, a neutron star, or a black hole. But white dwarfs and neutron stars have a strict upper limit to their mass. Beyond that limit, gravity overwhelms all other forces. An object this heavy had to have collapsed beyond the point of being a neutron star. It had to have crushed itself into a singularity. The final piece of the puzzle was the X-rays themselves. What was creating them? The prevailing theory provided a breathtakingly violent explanation. The blue supergiant star is so massive that its outer atmosphere is constantly being stripped away by stellar winds. The invisible companion's immense gravity captures this stream of gas, pulling it into a vast, swirling disk that spirals inward at nearly the speed of light. This accretion disk is a maelstrom of friction and colossal forces, heating the stolen stellar material to temperatures of millions of degrees. It is this incredibly hot, frenzied matter, just outside the event horizon, that glows not with visible light but with the searing energy of X-rays. We are not seeing the black hole itself. We are seeing the last desperate light show of matter being torn apart just before it vanishes forever from our universe. The discovery of Cygnus X-1 was a masterpiece of cosmic deduction, proving that we can indeed find these invisible titans by observing their devastating gravitational influence on everything that dares to come too close. But the existence of stellar mass black holes like Cygnus X-1 was just the beginning of the story. It hinted at an even more profound and monumental truth, one that would place a black hole not as a distant curiosity, but at the very core of our cosmic home. For centuries, we looked toward the center of our Milky Way galaxy and saw only a dense cloud of dust and gas, obscuring the light from whatever lay within. It was a mysterious blank spot on the map. Then we discovered what was lurking in that darkness, and it forced us to completely rewrite our understanding of galactic architecture. We now know that at the very heart of our galaxy, a silent, sleeping behemoth resides, a supermassive black hole named Sagittarius A star. To call this object massive is a dramatic understatement. While the black hole in Cygnus is a heavyweight at around 15 solar masses, Sagittarius A star is a true cosmic god, containing the mind-boggling mass of about 4 million suns, all crushed into a region of space no larger than our solar system. Contemplating such an object is a challenge for the human mind. Picture our own sun, which could contain 1.3 million Earths. Now multiply that by 4 million and imagine all that material concentrated into a single, unfathomably dense point. The gravity such an object generates is almost beyond comprehension, dictating the motion of every star, every nebula across the entire breadth of our galaxy. How could we possibly confirm the existence of something we cannot see? The proof came not from a single observation, but from a decades-long celestial ballet, a patient and meticulous study of the stars that dare to dance closest to the abyss. Astronomers, using increasingly powerful telescopes that can peer through the galactic dust, focused on a small patch of sky at the galactic center. They began tracking the motions of individual stars there, year after year, patiently mapping their paths. What they found was nothing short of spectacular. These stars were not drifting calmly. They were whipping around an invisible focal point at astonishing speeds, some completing wild, elongated orbits in just a few Earth years. One star in particular, known as S2, became a crucial key to the mystery. Its orbit is so tight that at its closest approach, it comes within a breathtaking 17 light-hours of the invisible center, a cosmic hair's breadth in galactic terms. At that point, it accelerates to a velocity of over 5,000 kilometers per second, nearly 2% of the speed of light. By applying the simple, timeless laws of orbital mechanics first laid down by Johannes Kepler centuries ago, scientists could calculate with absolute certainty the mass of the object that must be anchoring this frantic stellar dance. The math was unambiguous. To hold S2 and its stellar companions in such violent, precise orbits required an object with a mass of 4 million suns, confined to an impossibly small volume. The only known object in the universe that fits that description is a supermassive black hole. This was not a theory anymore, it was direct observational proof. We were watching stars orbit a ghost, and the ghost's immense weight revealed its terrifying nature. This discovery confirmed that black holes are not just stellar oddities. They are the fundamental engines, the gravitational anchors around which entire galaxies are built. This simple classification reveals a staggering cosmic hierarchy. At one end of the spectrum, we have the stellar mass black holes like the one in Cygnus X-1. These are the remnants of massive stars that have lived fast and died young in spectacular supernova explosions. They typically range from about 5 to perhaps 100 times the mass of our Sun. While their formation is a violent and dramatic process, it is one we understand reasonably well, governed by the life and death cycle of stars. But then we have their colossal cousins, the supermassive black holes like Sagittarius A, star at the center of our Milky Way. These are the true giants of the cosmos, boasting masses millions or even billions of times that of our Sun, all contained within a region roughly the size of our solar system. And here lies one of the greatest, most tantalizing mysteries in modern astrophysics. How did these behemoths get so big? The puzzle is a profound one of cosmic timescales. We see supermassive black holes in the very earliest epochs of the universe, when it was less than 1 billion years old. For a stellar mass black hole to grow to billions of solar masses in such a short time, it would have to consume matter at an impossibly frantic, unsustainable rate. A process that would generate so much radiation it would actually blow away the very material it's trying to feed on. It's like trying to grow a giant sequoia tree overnight. The known processes are just too slow. So, did these supermassive black holes start from gigantic seeds? Perhaps they formed from the direct collapse of enormous clouds of primordial gas in the early universe, bypassing the star stage entirely and collapsing into black holes weighing thousands of suns right from the start. Or could they be the result of frantic mergers, where early stars and smaller black holes collided and combined in the dense, crowded environments of the first galaxies? But the cosmic family portrait may be even more diverse. Bridging the enormous gap between the stellar mass and the supermassive, astronomers have been hunting for a third, elusive class, intermediate mass black holes. Imagine objects ranging from a few hundred to a few 100,000 solar masses. For a long time, they were the missing link, predicted by theory but frustratingly difficult to confirm. The breakthrough has come from observing the hearts of dense globular clusters, ancient, spherical swarms of hundreds of thousands of stars. In some of these clusters, the stars at the very center exhibit a distinct telltale wiggle, moving as if tugged by the gravity of a single, invisible object too heavy to be a stellar mass black hole, yet not nearly massive enough to be called supermassive. Then, in 2020, an even more dramatic signal was detected: gravitational waves from the collision of two black holes, one of which was about 85 solar masses. This was significant because it's thought to be difficult for a star to collapse directly into a black hole that heavy, leading to the compelling suggestion that this object was itself the product of an earlier merger, a potential building block for an intermediate mass black hole. Their existence would fill a crucial gap in our understanding of how the universe builds its largest structures, suggesting a gradual, hierarchical growth from small to immense over cosmic time. Now, this brings us to one of the most personal and terrifying questions about these cosmic giants. What would it actually be like to fall into one? The common image is one of instant, gruesome destruction, but the reality, governed by the unforgiving laws of physics, is far more nuanced and deeply depends on the size of the monster you encounter. This leads us directly to a phenomenon with a name as bizarre as the process itself: spaghettification. To understand this, we need to think about tidal forces. You experience a mild version of this every day thanks to our moon. The moon's gravity pulls more strongly on the side of the Earth facing it than on the center, and more strongly on the center than on the far side. This slight difference in pull stretches the Earth ever so slightly, and it's what causes our ocean tides. Now, magnify this difference in gravitational pull to an extreme that is almost impossible to comprehend. As you fall toward a black hole feet first, your feet are closer to the singularity than your head. In a small, stellar mass black hole, the gravitational gradient is incredibly steep. The difference in pull between your feet and your head would be astronomical. Your feet would be yanked downward with unimaginable force, while your head and torso would be pulled with slightly less force. The result, you wouldn't just feel stretched, you would be physically pulled apart, elongated into a thin stream of atoms long before you even reached the event horizon. You would literally become a human strand of spaghetti, hence the term. It would be a very quick and very terminal end to your journey, but the universe always has a surprise in store. If your destination were a supermassive black hole like Sagittarius, a star at the center of our galaxy, the experience would be radically different, at least in the beginning. Because a supermassive black hole is so immense, its event horizon is vastly larger. The crucial difference is that the gravitational gradient at this boundary is much more gentle. The difference in the gravitational pull between your feet and your head as you cross the event horizon would be negligible, perhaps even imperceptible. According to the pure mathematics of general relativity, you could cross this point of no return without even realizing it. There would be no flashing sign, no physical barrier, no immediate tearing sensation. You would simply and quietly pass from our universe into a region of space-time from which there is no return. This is where the physics becomes truly mind-bending. While you might cross the horizon unharmed, the fate that awaits you further inside is inescapable and ultimately just as destructive. As you continued your journey inward, the gravitational forces would begin to intensify. The gentle gradient would become steeper and steeper. Eventually, the tidal forces would become significant and the spaghettification process would begin. But here's the profound paradox. From your perspective, the traveler, this might all happen in a finite amount of time. You would be drawn inexorably toward the central singularity, stretched and compressed into oblivion. However, for an outside observer watching you fall, the story is completely different. Because of the extreme gravitational time dilation near the event horizon, they would see you slow down, appearing to freeze just at the threshold. Your image would become redder and dimmer, fading from view over what to them could be an eternity. You would seem to hover there forever, a ghostly testament to the warping of time itself. So, survival is a relative term. You might survive the crossing of the horizon, but you cannot survive the journey to the heart of the beast. This brings us to one of the most profound and personally unsettling consequences of a black hole's gravity, a phenomenon that strikes at the very heart of our experience of reality, the warping of time itself. We often think of time as a constant, universal river, flowing at the same steady rate for everyone and everything. But Einstein's theory of relativity shattered that comforting notion. It revealed that time is not absolute, it is malleable, a dimension that is intimately woven together with space and directly influenced by gravity. The stronger the gravitational field, the more time itself slows down. This effect, known as gravitational time dilation, is not just a theoretical curiosity, it's a measurable fact here on Earth. The clocks on GPS satellites orbiting high above our planet where Earth's gravity is slightly weaker actually run a tiny fraction of a second faster than clocks on the surface. Engineers must constantly correct for this drift, or your navigation system would lead you astray within minutes. Now, take this subtle effect and magnify it to the ultimate extreme at the edge of a black hole. To truly grasp this, let's follow the journey of two hypothetical astronauts. Imagine one brave explorer, let's call them Alex, volunteers to take a spacecraft and plunge directly toward a supermassive black hole. Their mission is to fly as close to the event horizon as possible, gathering data before firing their engines to escape. Their partner, Sam, remains at a safe distance in a mothership, observing Alex's descent through a powerful telescope. From Sam's perspective, watching from afar, something deeply strange begins to happen. As Alex's ship gets closer and closer to the immense gravitational field, Sam sees the ship's clock, which is broadcasting a signal, start to tick more and more slowly. The spacecraft itself appears to slow its descent, like a film being played at a gradually decreasing speed. The light coming from the ship gets stretched to longer, redder wavelengths, a phenomenon called gravitational redshift. As Alex approaches the event horizon from Sam's point of view, the ship seems to slow to an infinitesimal crawl. It appears to hover, frozen, just at the threshold. The clock's ticks become so slow that they are separated by years, then centuries, then millennia. Sam would never actually see the spacecraft cross the event horizon. From their external reference frame, it would take an infinite amount of time for that to happen. Alex would become a permanent, fading monument on the edge of eternity. But what is the experience like for Alex inside the spacecraft? This is where the paradox lies. For Alex, time passes completely normally. Their wristwatch ticks away second by second. Their heart beats at its regular rhythm. If they were to look out the window back toward Sam and the distant universe, they would see a very different scene. The light from the outside universe falling into the strong gravitational field with them would be blue-shifted and accelerated. The entire history of the cosmos might appear to flash before their eyes in a spectacular, blinding hurry. If Alex were to cross the event horizon, they would do so in a finite amount of their own personal time, perhaps only minutes or hours after beginning their final approach. They would not feel a sudden jolt or see a magical barrier. They would simply pass a point of no return, all while their own sense of time remains unchanged. This isn't a trick of perception or a malfunctioning clock. It is a fundamental feature of the universe. Time for the astronaut and time for the distant observer are literally different. Both perspectives are correct within their own reference frames. This incredible fact forces us to abandon the idea of a single, universal now. The passage of time is a personal experience, shaped and stretched by the gravity wells we find ourselves in. Yet even the mind-bending warping of time is only part of the story, because we have so far been describing a simplified, almost idealized version of a black hole, a static one. But the universe is a dynamic, spinning place, and black holes are no exception. In fact, most black holes are likely cosmic whirlpools, spinning at a significant fraction of the speed of light. This rotation transforms them from simple gravitational pits into far more complex and energetic engines. And to understand this, we need to move beyond the Schwarzschild solution to a new set of equations discovered decades later. The key insight comes from a fundamental principle of physics, the conservation of angular momentum. Think of an ice skater pulling their arms in during a spin. As their mass moves closer to their axis of rotation, they spin faster and faster. Now imagine a gigantic star many times the size of our Sun. Even if it seems to be turning slowly from our distant vantage point because it is so immense, it possesses a staggering amount of rotational energy. When that star collapses at the end of its life, it undergoes the most extreme version of the ice skater's pull. All that mass, which once spanned millions of miles, crushes down into a region perhaps only a few dozen miles across. To conserve its original spin, the nascent black hole must rotate incredibly fast. We are not talking about a leisurely rotation. Some black holes might be spinning at over 90% of the speed of light. This rotation fundamentally changes the black hole's structure, and the mathematics that describes this was first solved by New Zealand physicist Roy Kerr in 1963. The Kerr solution for a rotating black hole introduces a breathtaking new feature, the ergosphere. This is a region that lies outside the event horizon, an oblate, pumpkin-shaped zone of distorted spacetime that is arguably even more strange than the event horizon itself. Within the ergosphere, the black hole's furious rotation has such a powerful grip on the fabric of spacetime that it literally drags everything around with it. This phenomenon is known as frame dragging, and a mild version of it even occurs around our own rotating Earth, verified by precise satellite experiments. But at the edge of a spinning black hole, this effect is amplified to an absolute extreme. Inside the ergosphere, it becomes impossible to stand still. No matter how powerful your spacecraft's engines are, you cannot resist the current. You are forced to move in the direction of the black hole's spin, caught in a cosmic whirlpool from which there is no anchoring yourself. It's like being in a raging river where swimming against the current is not just difficult, it is fundamentally forbidden by the laws of physics. This leads to a remarkable possibility. Because the ergosphere lies outside the event horizon, it is theoretically a place you could enter and, if you had enough energy, still escape from. And within this region, the rotational energy of the black hole is up for grabs. In a theoretical process known as the Penrose process, an object could fly into the ergosphere and break apart in such a way that one piece falls into the black hole, while the other is flung outwards with more energy than the original object had going in. The escaping fragment essentially steals a portion of the black hole's rotational energy. This isn't magic, it's a direct consequence of the bizarre physics of the ergosphere. While this is likely not a practical way to power a civilization, it illustrates a profound truth. A spinning black hole is not just a sinkhole for matter and energy. It is a dynamic, powerful battery, its rotation imprinting itself on the very fabric of reality around it and offering glimpses into how we might one day harness the most extreme forces in the cosmos. This idea that a black hole acts like a cosmic vacuum cleaner, actively sucking in everything around it, is one of the most persistent and understandable misconceptions. It paints a picture of a malevolent, hungry force roaming the galaxy, pulling in stars and planets from vast distances. But the reality, as is so often the case with these cosmic titans, is both more subtle and more fascinating. A black hole does not possess some magical, extra-powerful sucking force. It exerts gravity in exactly the same way any other massive object does, governed by the same laws of physics that Isaac Newton and Albert Einstein described. It is simply an object with an immense amount of mass concentrated in an incredibly small volume. To truly grasp this, let's perform a thought experiment that seems terrifying but reveals a fundamental truth. Imagine that, in an instant, our sun were magically replaced by a black hole of exactly the same mass. What would happen to the Earth? The dramatic Hollywood version would have our planet immediately ripped from its orbit and spiraling inward to be devoured. But that is not what would occur. The key factor in orbital mechanics is mass, not the physical size or nature of the object. The Earth orbits the Sun because of the Sun's mass, which creates the gravitational well that our planet travels around. If you replace the Sun with a black hole of identical mass, the gravitational well remains exactly the same. The Earth would continue to orbit this new, dark center of our solar system in precisely the same path at the same speed, taking the same 365 days to complete its journey. The only difference, of course, is that it would get very dark and very cold quite quickly, as the source of our light and heat would be gone. But gravitationally, nothing would change. The planets would continue their silent, eternal dance around an invisible partner. So if a black hole isn't sucking things in, how do objects ever fall in? The process is one of losing energy, not being overpowered by a vacuum. Think about our own planet and the satellites that orbit it. A satellite in a stable low Earth orbit will eventually, over a long period, fall back to the ground. Is this because Earth suddenly increases its gravity? No, it's because the tenuous outer reaches of our atmosphere create a tiny amount of drag on the satellite. With each pass, the satellite loses a minuscule amount of orbital energy, slowing down just a little bit. This causes its orbit to decay, slowly spiraling lower and lower until it finally re-enters the atmosphere. A similar process happens around a black hole, but the drag isn't caused by an atmosphere. It's caused by the complex interactions within a structure we've already mentioned, the accretion disk. When a star or a cloud of gas ventures too close to a black hole, it doesn't get sucked in on a straight line. Instead, it begins to orbit the black hole, just as any object would around a massive body. However, in the incredibly crowded and violent environment near the event horizon, these orbits are chaotic. The infalling material forms a thick, swirling disk, and the individual particles within this disk are constantly colliding with each other, transferring energy and angular momentum. Through these collisions, some particles gain energy and are flung outward, while others lose energy. It is these unlucky particles, the ones that shed their orbital energy through friction and collisions, that are able to spiral inward, crossing the event horizon. They aren't pulled in, they fall in, much like a satellite slowly losing altitude until it can no longer maintain its orbit. This distinction is crucial. It means that a black hole is a passive gravitational object. It sits in space, warping the fabric of spacetime around it, and it's only the objects that stray too close and lose their orbital stability that ultimately meet their end within it. Yet, for all their apparent permanence, these gravitational titans may not be eternal fixtures of the cosmos after all. The seemingly immutable black hole, the ultimate endpoint from which nothing escapes, was challenged by one of the greatest minds of the 20th century, Stephen Hawking. He proposed a startling mechanism that suggests black holes can, in fact, lose mass and eventually evaporate completely. This idea, now known as Hawking radiation, bridges the two great pillars of modern physics: Einstein's theory of general relativity, which governs the very large, and quantum mechanics, which describes the bizarre world of the very small. The phenomenon hinges on a strange, well-documented quirk of the quantum vacuum. Empty space is not truly empty. Instead, it is a seething, bubbling sea of virtual particles. These are particle-antiparticle pairs that spontaneously pop into existence, borrowing energy from the universe for an impossibly brief moment before they collide and annihilate each other, paying back the energy loan. This constant, frantic activity is usually undetectable, as the pairs vanish almost as quickly as they appear. However, place this quantum frenzy near the immense gravitational gradient of a black hole's event horizon, and something extraordinary can happen. Imagine a virtual particle pair flickering into existence right at the precipice. The tidal forces are so extreme that the two particles can be ripped apart before they have a chance to annihilate. In this cosmic robbery, one particle falls into the black hole while its partner is ejected outward, escaping into the universe as a real particle. This escape comes at a cost, and the price is paid by the black hole itself. The universe demands its energy loan be repaid. The escaped particle carries positive energy away from the black hole. To balance the books, the particle that fell in must carry negative energy. In the language of gravity, adding negative energy to the black hole is equivalent to reducing its mass. So, with every pair of virtual particles separated in this way, the black hole loses a tiny, almost infinitesimal amount of mass. It's a slow, relentless leak. For a stellar mass black hole or a supermassive one, this process is so agonizingly slow that it is completely negligible. A black hole with the mass of our Sun would take a number of years so vast it's virtually meaningless, a 1 followed by 67 zeros, to evaporate. Over the current age of the universe, such black holes are, for all practical purposes, still growing by absorbing cosmic background radiation. But the story changes dramatically for a hypothetical class of black holes known as primordial black holes. These are not born from dying stars, but are thought to have been forged in the extreme density fluctuations of the Big Bang itself. They could be any size, and crucially, some could be very, very small. The rate of Hawking radiation is inversely proportional to the black hole's mass. The smaller the black hole, the hotter it is and the faster it evaporates. A primordial black hole with the mass of a small mountain would be emitting radiation at a tremendous rate. As it loses mass, it gets even smaller and hotter, causing the evaporation to accelerate in a runaway process that culminates in a final, colossal explosion, releasing the energy equivalent of millions of hydrogen bombs in a flash of gamma rays. While we have not yet confirmed the existence of these tiny black holes, their potential fate reveals a profound truth. Even the darkest, most seemingly eternal objects in the universe may ultimately meet their end not with a collapse, but with a whisper of quantum particles that builds to a final, spectacular bang. But if a black hole isn't a cosmic vacuum, what exactly is it doing with all that matter it captures? The answer transforms it from a passive gravitational well into the most powerful and efficient engine in the known universe. The key to this incredible power isn't the black hole itself, but the frantic, luminous whirlpool that forms just outside its event horizon, the accretion disk. This is where ordinary matter undergoes a transformation so violent and energetic that it outshines entire galaxies. To understand the sheer scale of this energy production, we need a point of comparison. For billions of years, stars like our Sun have been the benchmark for cosmic power plants. They generate energy through nuclear fusion, the process of forcing atomic nuclei together under immense heat and pressure. In the Sun's core, hydrogen atoms are fused into helium, and in that process, a tiny fraction of the mass is converted directly into energy, as described by Einstein's famous equation, E equals mc squared. But just how efficient is this stellar engine? The conversion rate for hydrogen fusion is remarkably low. Only about 0.7% of the mass involved is transformed into energy. It's a powerful process because the Sun is so enormous, but it's not particularly efficient. Now compare that to the environment around a black hole. As matter, be it gas, dust, or an entire star, is pulled into the gravitational grip, it doesn't fall straight in. Instead, it forms a rapidly spinning disk like water circling a drain. The particles in this disk are moving at relativistic speeds, creating immense friction and tidal forces that heat the material to temperatures we can scarcely comprehend, millions upon millions of degrees. This is where the efficiency becomes staggering. In this chaotic maelstrom, the conversion of mass into energy isn't happening through nuclear reactions alone. It's a combination of gravitational potential energy being released as the matter spirals inward and the sheer violence of particle collisions. The result is a process that can convert up to 40% of an object's mass directly into pure energy. To put that number in perspective, it is nearly 60 times more efficient than the fusion that powers stars. If you could take a single kilogram of material and feed it into a black hole's accretion disk, it would release the energy equivalent of burning millions of kilograms of coal or thousands of nuclear bombs. This is why quasars, the intensely luminous cores of distant galaxies powered by supermassive black holes, can outshine 1,000 Milky Ways combined, making them visible from the very edge of the observable universe. They are not just bright, they are the most consistently brilliant objects in existence, all thanks to the ultimate efficiency of gravity's last stand before the point of no return. And from these brilliant deductions and observations of the ghostly gravitational influence of black holes, we arrive at a moment that once seemed like pure science fiction, the day humanity opened its eyes and actually saw one. For decades, even as the evidence for black holes became undeniable, they remained abstract concepts defined by what was missing, the ultimate objects of darkness. That all changed in April 2019, when the Event Horizon Telescope collaboration unveiled an image that circled the globe, a picture that was immediately iconic, the first direct visual evidence of a black hole's shadow, a fiery ring of light surrounding the profound darkness of the event horizon of the supermassive black hole at the heart of the galaxy Messier 87. What you are seeing in that now famous image is not the black hole itself, of course. No light can escape from it to be captured by any telescope. Instead, you are witnessing the black hole's silhouette, its shadow cast against the brilliant, swirling backdrop of its own superheated accretion disk. The intense gravity bends the light from the disk behind it, wrapping it around the event horizon to create a perfect or nearly perfect circle of fire. The dark central region is about 2.5 times larger than the actual event horizon, a direct confirmation of the predictions made by Einstein's equations over a century ago. It was a monumental validation not just of the existence of black holes, but of our fundamental understanding of gravity itself. We weren't just looking at an artist's impression anymore. We were looking at data, a direct observation of the warped spacetime around a singularity 6.5 billion times more massive than our Sun. The sheer audacity of this achievement cannot be overstated. The black hole in M87 is 55 million light-years away. Resolving its event horizon from that distance is the equivalent of standing in New York and reading the date on a coin in Los Angeles, or counting the ridges on a golf ball on the surface of the moon. No single telescope on Earth possesses that kind of resolving power. The solution was as brilliant as it was complex: to turn the entire planet into one giant telescope. The Event Horizon Telescope is not a single instrument, but a global network of 8 radio observatories, synchronized by atomic clocks to observe the same patch of sky at the exact same time. By combining the data from telescopes spanning from the volcanoes of Hawaii to the mountains of Spain and the frigid heights of the South Pole, the collaboration effectively created a virtual telescope dish the size of Earth itself. This technique, known as very long baseline interferometry, allowed them to achieve an angular resolution sharp enough to see the shadow of the abyss. The process of capturing the image was only half the battle. The amount of raw data collected was staggering, so vast it couldn't be sent over the internet. The hard drives containing the observations from the South Pole telescope had to be physically flown out at the end of the winter season. This raw data was then combined and processed by supercomputers in a painstaking effort that took years, as teams around the world worked to calibrate and clean the signals, essentially stitching together the fragments of light captured by each telescope to reconstruct the final, breathtaking picture. The result was more than just a pretty picture. It was a precise measurement that allowed scientists to test the very limits of general relativity in an environment of extreme gravity, and Einstein's theory passed with flying colors. It proved that even under conditions he could never have imagined, his description of the universe holds true, revealing a cosmos that is both stranger and more beautifully ordered than we ever dreamed. But the true legacy of that first image of M87 goes far beyond a single snapshot. It was the opening of a new window on the universe, proving that we could directly observe the environment around these enigmatic objects. Yet there is another, even more profound way to sense their presence, not by seeing the light they influence, but by feeling the very fabric of the cosmos shudder with their movements. We are talking about the detection of gravitational waves, the ripples in spacetime predicted by Einstein a century ago, and the story of their discovery brings us to one of the most violent and energetic processes in existence, the merging of two black holes. For decades, the idea of gravitational waves remained in the realm of theory. Einstein himself was unsure if these faint ripples would ever be detected, as he thought they would be too weak to measure. The concept is a direct consequence of his theory of general relativity. Just as a moving electric charge creates ripples in the electromagnetic field, what we call light, any accelerating mass creates ripples in the gravitational field, which is the curvature of space-time itself. Imagine the universe as a vast, still pond. If you gently place a bowling ball on its surface, it will create a deep, stationary dimple. This is like a star warping space. But if you were to take two bowling balls and swirl them around each other, they would send out waves across the pond's surface. In the cosmos, the most massive and rapidly accelerating objects, like orbiting black holes or neutron stars, create these waves in the fabric of space-time. They are not waves through space, they are waves of space itself, rhythmic stretches and squeezes of the very distance between points. The challenge was that by the time these ripples reached Earth after traveling for millions or billions of light years, they were unimaginably tiny, changing the distance between objects by less than the width of a proton. Detecting such a minuscule effect seemed nearly impossible. That was the monumental task undertaken by the Laser Interferometer Gravitational Wave Observatory, or LIGO. It consists of two colossal facilities in the United States, separated by nearly 2,000 miles. Each facility is built in the shape of an L with two arms, each 4 kilometers long. Inside these vacuum tubes, a powerful laser beam is split and sent racing down each arm, reflecting off mirrors to travel back and recombine. In perfect stillness, the laser light waves are tuned to cancel each other out. But if a gravitational wave passes through the Earth, it will infinitesimally stretch one arm of the detector while squeezing the other, just for a fraction of a second. This change, smaller than the diameter of an atomic nucleus, alters the laser light's path just enough to create a flicker of light at the detector, a signal. On September 14, 2015, after decades of design and refinement, that signal finally arrived. Both LIGO detectors in Louisiana and Washington state recorded an unmistakable chirp, a rising frequency and amplitude that lasted only 0.2 of a second. The signal perfectly matched the predictions for the final moments of a cosmic dance of death. Over 1 billion light-years away, two black holes, one about 36 times the mass of our Sun and the other 29, had been orbiting each other. As they spiraled closer, they lost energy by radiating it away as gravitational waves, a process that accelerated their inward plunge. In the last frantic moments before the collision, they whirled around each other hundreds of times per second, and then, in an instantaneous cataclysmic merger, they became a single, more massive black hole. The energy released in that final moment was staggering. For a brief flash, the power output in gravitational waves exceeded the combined light of every star in the observable universe. The merger converted 3 whole solar masses of matter directly into pure energy, according to E equals mc², a conversion efficiency that dwarfs anything else known. The new black hole, 62 solar masses, settled down, ringing like a bell, its gravitational wave signature fading away as quickly as it came. This event, labeled GW150914, was not just the first direct detection of gravitational waves, it was the first direct observation of a binary black hole system and its violent merger, opening an entirely new field of astronomy where we can now listen to the symphony of the universe. This leads us to a hypothesis so profound it could solve 2 of the universe's greatest mysteries with a single, elegant idea. We've been talking about the black holes we can see, or at least detect by their influence on light and matter. But what if the cosmos is teeming with a hidden population of black holes, so numerous and widespread that their collective gravity shapes the fate of galaxies? This is the tantalizing possibility that some, or perhaps even all, of the mysterious substance we call dark matter could be made of black holes. Not the giant ones we find in galactic centers, but a vast, invisible swarm of small, ancient ones known as primordial black holes. To understand why this idea is so compelling, we first need to recall the dark matter puzzle. For nearly a century, astronomers have known that the universe contains far more mass than we can see. Galaxies rotate so fast that the visible stars and gas within them should be flung apart. They only hold together because of the gravitational pull of an enormous amount of invisible matter that surrounds them like a ghostly halo. We call this missing mass dark matter. We know it's there because of its gravity, but we have no idea what it's actually made of. For decades, the leading candidates have been exotic, hypothetical subatomic particles like WIMP or actions that barely interact with normal matter. But despite enormous efforts, not a single one of these particles has ever been detected. This persistent failure has led scientists to re-examine a fascinating alternative that doesn't require any new physics beyond Einstein's gravity: primordial black holes. The key difference lies in their origin. Stellar mass black holes are born from the death of massive stars, which means they couldn't have existed in the very first moments after the Big Bang. Primordial black holes, however, are thought to be a product of the Big Bang itself. In the incredibly hot, dense soup of the infant universe, tiny regions of space could have been so tightly packed that their own gravity caused them to directly collapse. There was no star, no supernova, just a raw overdensity in the fabric of spacetime that pinched off into a black hole. These objects could have formed with a staggering range of masses. Some might have been as light as an asteroid, while others could have contained the mass of thousands of suns. Crucially, if conditions were just right in the early universe, they could have been produced in absolutely enormous numbers, forming a vast, unseen ocean of black holes that permeates every galaxy. The beauty of this idea is its simplicity. It explains the gravitational effects of dark matter with objects we already know exist, governed by laws of physics we already understand. We wouldn't need to invent new particles. The mystery matter would simply be ordinary atomic matter that collapsed into black holes in the first fraction of a second of time. But a grand idea like this requires grand evidence, and the hunt for these phantom black holes is one of the most creative endeavors in modern astronomy. Since they would emit virtually no light, especially the smaller ones that would have evaporated away by now due to Hawking radiation, we cannot look for them directly. Instead, astronomers search for them using a cosmic phenomenon predicted by Einstein: gravitational lensing. According to general relativity, any massive object warps the space around it, bending the path of light that passes nearby. A primordial black hole drifting through space would act like a tiny, invisible lens. If one were to pass directly between Earth and a distant star, its gravity would briefly focus and amplify the star's light, causing the star to appear to brighten for a short period before fading back to normal. This event is called a microlensing event. Several ambitious projects like the Optical Gravitational Lensing Experiment, or OGLE, and the Massive Astrophysical Compact Halo Object Survey, or MACHO, have spent years monitoring millions of stars in nearby galaxies, like the Large Magellanic Cloud, searching for these telltale flashes. They have found some lensing events suggesting the presence of compact, massive objects in the halo of our galaxy, but the numbers haven't yet added up to account for all the dark matter. The mystery persists, and the search continues with even more powerful tools, scanning the heavens for the subtle, fleeting signatures of these ancient ghosts from the dawn of time, whose collective weight may be the invisible hand guiding the motion of the cosmos. But this idea of a black hole as a simple, three-property object leads us to one of the most elegant and potentially flawed concepts in theoretical physics: the no-hair theorem. The name itself is a metaphor suggesting that a black hole, unlike a person, has no distinguishing features or intricate details, no hair. After all the violent chaos of its formation, after swallowing stars, planets, and entire clouds of gas, the theorem proposes that a black hole settles down into an astonishingly simple state. According to this idea, you can describe any black hole completely using just three, and only three, numbers: its mass, its electric charge, and its spin or angular momentum. Everything else, the type of matter that fell in, whether it was made of pianos or protons, ice cream or iron, is irretrievably lost. The black hole, in this view, is the ultimate cosmic eraser. It shaves off all the complicated information about what made it, presenting a perfectly bald, featureless face to the outside universe. This mathematical elegance was deeply appealing, suggesting that in their final form, black holes are the simplest objects in existence. However, this beautiful simplicity created a monumental conflict with another cornerstone of physics: quantum mechanics. Quantum theory states that information about the state of a physical system can never be truly destroyed. It might be scrambled into an unrecognizable form, but in principle, it should always be possible to recover it. This is a fundamental tenet often called the conservation of information. The no-hair theorem, by declaring that all information is lost forever behind the event horizon, directly contradicts this. This clash became known as the black hole information paradox, a problem that has puzzled physicists for decades. If information is lost in a black hole, it undermines the very predictability that is the foundation of science. We could never know the past completely if black holes are allowed to erase it. Stephen Hawking himself highlighted this paradox, famously arguing that information is destroyed, a stance that led to a famous bet he eventually conceded, though the solution remained elusive. The paradox seemed to force a choice: either our understanding of gravity and black holes was wrong, or quantum mechanics was incomplete. This is where the idea of quantum hair enters the story, a fascinating and recent theoretical development that might just offer a way out of this impasse. The term is a clever play on the no-hair theorem, suggesting that while black holes may not have hair in the classical sense of general relativity, they might possess a faint, subtle fuzziness at the quantum level that encodes information. The key insight is that the event horizon itself may not be the perfectly smooth, featureless surface the no-hair theorem describes. Instead, quantum fluctuations and corrections to gravity might imprint the black hole with a unique structure, a kind of fingerprint that depends on the specific history of what fell into it. Imagine throwing two different objects into a black hole, one made entirely of iron, another made of carbon. According to the classical theorem, the final black hole would be identical in both cases. But with quantum hair, the gravitational field of the black hole might be minutely different. Perhaps the way space is curved just outside the horizon holds a subtle echo, a quantum memory of what created it. This isn't about finding the lost atoms inside the hole. It's about the idea that the information they contained is not trapped inside, but is somehow smeared out or encoded onto the surface of the event horizon itself. Think of it like this: if you burn a book, the information in it seems lost. But in principle, if you could collect every single smoke particle and ash fragment and analyze their state with impossible precision, you could reconstruct the book. The information was never destroyed, it was just transformed into a vastly more complex state. Quantum hair proposes a similar mechanism for black holes. The information about the ingested matter isn't vanished, it's imprinted into the intricate quantum properties of the horizon. This concept provides a potential pathway to resolve the information paradox, suggesting that information is, in fact, preserved and might even be slowly leaked back out into the universe through the subtle processes like Hawking radiation, ensuring that the cosmic ledger of information remains balanced after all. Yet, even as we contemplate how a black hole might erase information, we are drawn to an even more spectacular possibility that rather than being a final destination, a black hole could be a gateway. This idea emerges directly from the same equations that predict black holes in the first place. When Albert Einstein and his colleague Nathan Rosen explored the mathematical implications of general relativity in the 1930s, they found that the theoretical structure of a black hole could be extended to form a bridge, a tunnel connecting two distant points in spacetime. This theoretical passageway is known as an Einstein-Rosen bridge, though you likely know it by its more popular and evocative name, a wormhole. Picture the universe not as a flat sheet, but as the surface of an apple. To travel from one side of the apple to the other, an ant would have to walk the long way around the curved surface. But if the ant could burrow directly through the apple's core, it would create a much shorter, faster tunnel. A wormhole is the cosmic version of that tunnel. It would have two mouths, each acting as an entrance and exit, connected by a narrow throat. The incredible implication is that one mouth could be right here in our solar system, while the other could be in a galaxy billions of light years away, or even in a completely different universe altogether. The journey through the throat could, in theory, take a fraction of the time it would take to travel the long way through normal space, making it the ultimate shortcut for interstellar travel. The connection to black holes is profound. The mathematics suggest that the interior of a black hole, specifically the singularity at its heart, might not be a dead end. Instead, it could potentially be the very throat of a wormhole, connecting to a corresponding object known as a white hole. If a black hole is a point of no return where matter and energy can only fall in, a white hole would be its exact opposite, a point of no entry where matter and energy can only spew outward. Nothing could ever enter a white hole. It would be a cosmic fountain, eternally expelling material. In this breathtaking scenario, if you were to survive the journey through a black hole, you might not be crushed into oblivion. You could be flung out of a white hole into another region of space, or into an entirely separate cosmos. It is crucial to emphasize that this remains firmly in the realm of high theory and mathematical speculation. There are immense physical problems with this idea. First and foremost is the issue of stability. The kind of wormhole predicted by the classic Einstein-Rosen solution would be incredibly unstable. The throat of the wormhole would likely pinch shut faster than the speed of light, preventing anything from ever passing through. To keep a wormhole open and traversable, you would need a form of matter with truly exotic properties, something often called exotic matter, which would possess negative energy density. This isn't antimatter. Antimatter has positive energy. This would be a substance that somehow repels gravity rather than attracts it, propping the wormhole's throat open against its natural tendency to collapse. Whether such matter can exist, and in sufficient quantities, is one of the great unanswered questions in physics. So, while the image of a black hole as a portal to another reality is a staple of science fiction and a fascinating consequence of Einstein's equations, it is not something we have any evidence for in the observed universe. But its power lies in pushing our imaginations to the limit, forcing us to ask what might be possible in the most extreme environments nature can concoct. It suggests that the cosmos might be far more interconnected and far stranger than we ever dreamed. This symbiotic relationship between a supermassive black hole and its galaxy is one of the most important discoveries in modern cosmology, fundamentally changing our view of galaxies from isolated islands of stars to dynamic ecosystems regulated by a hidden heart. For a long time, it was a mystery why galaxies seemed to come in two broad flavors: vibrant, spiral galaxies brimming with young blue stars and ongoing star formation, and massive, red and dead elliptical galaxies where star formation had effectively ceased. The answer appears to lie in the activity cycle of the central black hole. When a galaxy is rich with gas, some of that fuel spirals inward, feeding the black hole and igniting its accretion disk into an brilliant quasar or active galactic nucleus. This is a period of phenomenal energy output, but it's also a period of self-regulation. The energy released by this feasting black hole doesn't just create light, it creates powerful outflows. Think of it as the galaxy's central heating system turning on with explosive force. These outflows can take two forms. The first are vast winds of hot gas blown outward from the accretion disk at tremendous speeds, sweeping through the galactic core. The second, and even more dramatic, are the relativistic jets, twin beams of charged particles shooting out from the poles of the black hole at nearly the speed of light, often extending for thousands of light years beyond the galaxy itself. These jets pump colossal amounts of energy into the surrounding intergalactic medium, the thin soup of gas that exists between galaxies. This process, known as feedback, has a profound consequence. It heats up the galactic gas reservoir, preventing it from cooling down, collapsing under its own gravity, and condensing into new stars. In this way, the supermassive black hole acts as a cosmic thermostat. A period of intense feeding and activity effectively shuts down the very process that might have continued to feed it. By heating or even blowing away the surrounding gas, the black hole starves itself, quenching star formation across the entire galaxy and leading it to mature into a quiet, elliptical galaxy. Without this feedback mechanism, our models suggest that galaxies would continue to form stars at a frantic pace, growing far larger and more massive than the ones we actually observe. The black hole, therefore, is not a passive occupant. It is an active governor, its growth intimately tied to the growth of the galaxy itself. Observations now show a remarkable correlation between the mass of a galaxy's central bulge of stars and the mass of its supermassive black hole. The two grew up together, the black hole's ferocious youth ultimately putting a cap on the size of its cosmic home. And yet, even the supermassive black holes that govern entire galaxies are not the final word on cosmic scale. Beyond the behemoths like Sagittarius A, there exists a class of objects so colossal that they defy easy comprehension. To encounter one of these true giants, we must journey far beyond our local galactic neighborhood, out into the deep reaches of the observable universe to an object known as TON 618. This is not just a black hole, it is a hyperluminous quasar, a beacon of unbelievable power, and at its heart lies the single most massive black hole ever discovered. The numbers associated with TON 618 are so vast they almost lose their meaning. Current estimates place its mass at a staggering 66 billion times that of our Sun. To put that in perspective, the supermassive black hole at the center of our Milky Way would be a mere speck, a tiny pebble next to a mountain, 66 billion suns. Contemplate the sheer weight of that statement. Our entire solar system, from the Sun out to the distant Oort cloud, is an insignificant dot compared to the gravitational dominion of this single entity. The true scale of this monster is best understood not by its mass, but by the sheer volume of space it commands. The defining boundary of any black hole is its event horizon, the point of no return. The size of this sphere is known as the Schwarzschild radius. For our Sun, this theoretical boundary would be a mere 3 kilometers across. For the black hole in Cygnus X-1, it would be about 100 kilometers. For Sagittarius A, it expands to roughly the distance between the Sun and Mercury. But for TON 618, the Schwarzschild radius is a realm of pure fantasy. The event horizon of this black hole would have a diameter larger than our entire solar system. If you were to place TON 618 where our Sun is, its event horizon would stretch outward, engulfing the orbits of every single planet and continuing far, far beyond the orbit of Pluto. It would swallow the Kuiper belt and extend deep into the scattered disk of icy objects at the solar system's edge. The shadow it casts is not a dot, it is an abyss wide enough to contain thousands of worlds. What powers such an unimaginable object? TON 618 is a quasar, the intensely bright active galactic nucleus of a distant galaxy. The light we see from it, which has been traveling for over 10 billion years to reach us, is the glow of its gargantuan accretion disk. The amount of matter being shredded and superheated as it spirals into this cosmic vortex is beyond belief. the luminosity of ton 618 is equivalent to that of more than 100 trillion suns, outshining our entire Milky Way galaxy by many thousands of times. This is the energy output of a black hole feasting on a continuous supply of gas, dust, and perhaps even entire stars, on a scale that is almost impossible to conceive. The existence of such a titan in the early universe also presents a profound challenge to our models of cosmic evolution, forcing us to ask how something could grow so massive so quickly after the Big Bang. Ton 618 stands as a testament to the fact that in the cosmos, our definitions of large and powerful are always relative, and that the universe is capable of creating structures whose scale humbles even our wildest imaginations. This leads us to one of the most delightful paradoxes about these cosmic marvels, the idea that they aren't actually black at all. Certainly, the black hole proper, the event horizon and the singularity within, is the ultimate embodiment of darkness, a region from which no light can ever escape. But to focus only on that is like judging a powerful engine by its exhaust pipe while ignoring the fiery combustion chamber. The immediate environment surrounding a black hole is often the exact opposite of dark. It can be one of the most violently luminous and energetic places in the entire cosmos. The key, as we've touched on, is the accretion disk. When a black hole, especially a supermassive one, is actively feeding on surrounding gas, dust, or even entire stars, the material doesn't just vanish quietly. It forms a frantic, whirling maelstrom just outside the point of no return. The friction and tidal forces within this disk heat the matter to temperatures of millions of degrees, causing it to glow with an intense, blazing light across the electromagnetic spectrum, from radio waves to X-rays. This is the engine that powers the most consistently brilliant objects we have ever observed, quasars. The term quasar is short for quasi-stellar radio source, a name that comes from their initial, puzzling appearance in telescopes as star-like points of light that curiously emitted strong radio waves. We now understand that a quasar is not a star at all. It is the incredibly bright, active galactic nucleus of a distant galaxy, a beacon whose core is a supermassive black hole in the midst of a colossal feast. The light from a quasar is the radiance of its accretion disk, a disk so vast and so energetic that it can outshine the combined light of every single star in its host galaxy. To put that in perspective, a single quasar can be thousands of times more luminous than a galaxy like our Milky Way, which contains hundreds of billions of stars. This makes quasars visible from the very edge of the observable universe, their light having traveled for billions of years to reach us, acting as cosmic lighthouses from the early epochs of cosmic history. They are a testament to the unbelievable efficiency of gravitational energy conversion, where matter plunging toward oblivion unleashes a final, spectacular scream of light before it vanishes forever. But the brilliance doesn't stop with the accretion disk itself. Many active black holes exhibit another, even more extreme phenomenon, the eruption of relativistic jets. These are narrow, focused beams of ionized matter that are shot outward from the regions near the black hole's poles, traveling at velocities achingly close to the speed of light. The exact mechanism that creates these jets is a topic of intense study, but it's thought to be intimately linked to the black hole's spin and its powerful magnetic fields. As matter spirals in the accretion disk, immense magnetic fields are generated and wound up like cosmic springs. Some of the infalling material, instead of crossing the event horizon, gets channeled and accelerated along these magnetic field lines, erupting from the poles of the system in a spectacular, concentrated eruption. These jets can extend for hundreds of thousands, even millions of light years into intergalactic space, far beyond the confines of their host galaxy. When these jets are pointed nearly directly at Earth, we observe them as particularly bright objects known as blazars. The particles within these jets, moving at relativistic speeds, interact with magnetic fields and ambient light, causing them to glow brilliantly across many wavelengths. So, while the black hole itself is a perfect black sphere, it can be the anchor for a structure of light so immense it dwarfs the galaxy it resides in, a pair of searchlight beams that illuminate the cosmos on a truly monumental scale. But this elegant simplicity, this baldness of the black hole, creates one of the most profound and enduring conflicts in all of modern physics, a puzzle known as the black hole information paradox. At its heart is a fundamental clash between the two great theories that describe our universe, Einstein's general relativity and quantum mechanics. General relativity, which gives us the beautiful picture of warped spacetime and event horizons, seems to suggest that information is irrevocably lost. When an object, let's say a book or an entire star, falls into a black hole, all the specific details that made it what it was are seemingly erased. The black hole's mass, charge, and spin increase, but the information about whether it consumed something made of iron or gold, water or diamonds is gone. The universe, according to this view, has a truly terrible memory. Quantum mechanics, the rules governing the subatomic world, paints a completely different picture. One of its most sacred principles is the conservation of information. This isn't about saving data on a hard drive, it's a fundamental statement about causality and predictability. In the quantum realm, information about the state of a particle can never be truly destroyed. It might be scrambled, transformed, or hidden in correlations between particles, but it is always, in principle, recoverable. If you could somehow reverse all the motions and interactions of every particle in a system, you could wind time backward and see exactly how it started. This principle ensures that the universe is predictable. The black hole information paradox throws a wrench into this entire framework. If a black hole truly destroys information, then it creates a scenario where identical initial states, two black holes with the same mass, charge, and spin, could have been formed from completely different collections of matter. The past becomes unknowable, and the fundamental predictability of physics breaks down. This paradox is not just a philosophical curiosity, it points directly to a glaring gap in our understanding. General relativity and quantum mechanics are both spectacularly successful in their own domains, the cosmically large and the vanishingly small, but they are fundamentally incompatible. The intense gravity at the heart of a black hole is exactly the environment where both theories should be needed, and yet, when applied together, they produce this logical contradiction. This tells physicists that we are missing a deeper theory, a unified framework often called quantum gravity, which would seamlessly blend the rules of the very small with the geometry of the very large. The information paradox is the clearest signpost we have, pointing toward this next great revolution in physics. So, how might this paradox be resolved? One of the most mind-bending and promising ideas is the holographic principle. This concept suggests that the information about everything that falls into a black hole is not lost inside its volume, but is instead encoded on its surface, the event horizon. Think of it like a cosmic DVD. A three-dimensional movie is stored on the two-dimensional surface of the disk. The holographic principle proposes a similar mechanism for the universe. All the information about the three-dimensional objects that have fallen into the black hole could be preserved in a scrambled, two-dimensional form on the event horizon. In this view, the horizon is not a smooth, featureless boundary, but a vast, complex tapestry storing an almost unimaginable amount of data. This leads to an even more radical implication. If the information is stored on the boundary, then the true degrees of freedom, the fundamental stuff of the universe, might actually exist in two dimensions, and the three-dimensional world we experience, including the interior of the black hole, could be a projection, a hologram emanating from that lower dimensional surface. This doesn't mean our reality is an illusion, but that its description might be far more economical and strange than we ever imagined. the information isn't destroyed, it's translated. When Hawking radiation slowly evaporates the black hole, this theory suggests the information is gradually and chaotically released back into the universe, ensuring the cosmic ledger remains balanced. While the holographic principle is still a developing concept, it represents a breathtaking attempt to solve the information paradox, suggesting that the key to understanding the deepest secrets of black holes lies not in looking into the abyss but in reading the surface. While the Penrose process remains a brilliant thought experiment, it's a stark reminder that these cosmic titans are not just destructive, they are also potential powerhouses of almost unimaginable scale. The energy we're talking about isn't chemical or even nuclear, it's the raw rotational energy of spacetime itself. This leads to an even more astonishing theoretical concept, one that dwarfs even the Penrose process in its sheer ambition, the black hole bomb. Also known as the superradiant scatter, this idea was first proposed by Russian physicist Yakov Zeldovich in the 1970s. It envisions a way to amplify light waves using a rotating black hole, turning it into the ultimate energy amplifier. The mechanism relies on a phenomenon called superradiance. Just as the Penrose process extracts rotational energy from the ergosphere, superradiance suggests that certain waves, like light or gravitational waves, can also steal energy if they scatter off the black hole's ergosphere under the right conditions. A wave with a specific frequency that hits the spinning ergosphere can be reflected back with more energy than it arrived with. The black hole's rotation imparts extra energy to the wave, causing it to bounce away amplified. Now, imagine taking this natural amplifier and building a containment system around it. The theoretical black hole bomb involves constructing a gigantic spherical mirror around the rotating black hole, enveloping the entire ergosphere. If you then introduce a single photon of light inside this mirror, something extraordinary would happen. The photon would bounce off the mirror, strike the ergosphere, and be amplified through superradiance. It would then reflect off the mirror again, return to the ergosphere, and be amplified even further. This process would create a runaway feedback loop. With each pass, the light wave would grow exponentially in energy, building up inside the spherical mirror until the containment vessel could no longer hold it, resulting in a catastrophic explosion that would release more energy than every star in a galaxy combined. Of course, building a mirror capable of containing such forces is far beyond any conceivable technology, and the entire concept resides firmly in the realm of theoretical physics. But its significance lies in what it reveals. A rotating black hole is not just a source of energy we can passively tap. It can act as an active engine for amplification, a cosmic battery that could, in theory, be triggered to release its stored power on a scale that redefines the word power itself. This relentless conflict between the rules of the cosmos and the rules of the quantum world brings us to the ultimate challenge that black holes present, one that goes far beyond mere scientific curiosity and strikes at the very foundation of our understanding of reality itself. Black holes are more than just cosmic objects. They are profound philosophical puzzles, forcing us to confront the absolute limits of our current physical theories. The heart of this challenge lies in the singularity, that enigmatic point at the center of a black hole where density becomes infinite and the curvature of spacetime soars to an infinite value. In the language of mathematics, this is where our equations spit out results that are nonsensical, like dividing by zero. It is a clear and undeniable sign that our theories, which work so beautifully everywhere else, are incomplete. They are cracking under the pressure of the most extreme conditions the universe can concoct. Think of our two great pillars of physics as different languages, each perfectly suited for describing its own domain. On one hand, we have Albert Einstein's general relativity, the magnificent theory that describes gravity as the curvature of spacetime. It is the language of the cosmos, explaining the orbits of planets, the bending of light, and the expansion of the universe with stunning accuracy. It paints a smooth, continuous picture of reality like a vast, flexible canvas. On the other hand, we have quantum mechanics, the rulebook for the subatomic world. It describes a reality that is grainy, probabilistic, and wildly unpredictable, where particles can be in two places at once and pop in and out of existence. This theory has been equally successful, underpinning everything from the chemistry of life to the technology in our phones. The problem is, these two languages are fundamentally incompatible. They speak about the universe in ways that cannot be easily translated into one another. A black hole is the only place in the universe where both of these theories are screaming to be used at the same time, and their conflicting voices create a cacophony of paradoxes. To understand the immense gravitational field and the warping of spacetime on a large scale, we need general relativity. But to understand the fate of matter and information crushed into an infinitesimally small point, the singularity, we need quantum mechanics. We are trying to use a weather map to forecast the path of a single raindrop, or a microscope to chart the course of a hurricane. The singularity is the ultimate physical paradox, a place where the smooth fabric of relativity must somehow reconcile with the fuzzy, quantized nature of the quantum world. It is a breakdown so complete that it is not a failure of our calculations, but a beacon pointing toward a deeper truth we have yet to uncover. This makes black holes the most extreme natural laboratories in the universe. We cannot recreate their conditions on Earth, but we can observe them and use their bizarre properties to test the boundaries of our knowledge. They are the cosmic crucibles where the next great theory of physics, often called quantum gravity, must be forged. This sought-after theory would be the unified language, the grand framework that seamlessly blends the world of the very large with the world of the very small. It would tell us what truly happens at the center of a black hole, not with infinities, but with a new, more complete set of rules. The information paradox we discussed is not just a problem, it is the most important clue we have in this quest. It is the universe's way of showing us exactly where our current understanding fails, providing a specific, sharp-edged puzzle that any theory of quantum gravity must be able to solve. By staring into the darkness of the event horizon, we are not just looking at a black hole. We are looking at the frontier of human knowledge, a place where our current map of reality ends and the true adventure of discovery begins. Contemplating the scale of the cosmos often leads us to count stars, those brilliant pinpricks of light that number in the hundreds of billions within our Milky Way alone. But this familiar census misses the true, darker population of our galaxy. The staggering fact is that the number of black holes, the invisible remnants of dead stars, almost certainly dwarfs the number of stars you can see. For every sun-like star shining in the night sky, there are countless ghosts lurking in the darkness. To understand why, we need to look at the life cycle of stars. Only a small percentage of stars are massive enough to end their lives in the supernova explosions that create stellar mass black holes. But given the sheer number of stars that have been born, lived, and died over the 13.8 billion-year history of the universe, that small percentage translates into an absolutely colossal number. Conservative estimates suggest there could be over 100 million stellar mass black holes drifting silently through our galaxy, and some models propose that number could be in the billions. Each one is a monument to a giant star that once burned brightly before collapsing in on itself. Now expand that thought beyond the confines of the Milky Way. Our galaxy is just one of an estimated 2 trillion galaxies in the observable universe. If each of those galaxies contains even 100 million black holes, the total number becomes a figure so vast it challenges comprehension. We are talking about a number like 10,000 billion, or a 1 followed by 22 zeros. This invisible population forms a pervasive, hidden architecture within the cosmos. They are the gravitational anchors in the dark, their collective mass woven into the fabric of every galaxy. And this doesn't even include the supermassive black holes that almost every large galaxy harbors at its center, or the potential multitude of primordial black holes that may have formed in the first instant after the Big Bang. So, when you gaze up at the starry sky, try to shift your perspective. See not just the points of light, but the profound darkness between them. For in that darkness, the true silent majority of the universe resides, a countless host of gravitational ghosts that outnumber the shining stars. Yet, even as we learn to see these colossal objects, we are simultaneously opening an entirely new sense with which to perceive them, moving beyond the silent movie of light into the realm of cosmic sound. This new sense allows us to literally hear the universe, and the songs it sings are the ripples in space-time created by the most violent events in existence. The detection of gravitational waves, those faint whispers from colliding black holes, didn't just give us a new signal. It gave us a new way to listen to the cosmos, translating the vibrations of space-time itself into sounds we can perceive. Think of it not as hearing with your ears, but as feeling the deepest bass notes of the universe's symphony through the very fabric of reality. The process begins with the raw data from observatories like LIGO and Virgo. The signal they capture is not a sound wave traveling through air. It's a precise measurement of how the distance between 2 points infinitesimally stretches and squeezes as a gravitational wave passes through. This data is a complex waveform, a squiggle on a graph that tells a story of acceleration and mass. To make this accessible, scientists shift the frequency of these waves into the range of human hearing. It's akin to taking a recording of a whale song, which is at a very low frequency, and speeding it up so we can hear its intricate structure. When they do this with the signal from a black hole merger, the result is unmistakable, a rising chirp. It starts as a low hum, representing the black holes orbiting each other at a great distance. As they spiral closer, losing energy to gravitational waves, their orbital speed increases and the pitch of the chirp swiftly rises. The amplitude or volume also grows, reflecting the increasing power of the waves as the black holes get closer and accelerate. Then, at the very peak of the chirp, there is a sudden, bright whoop, the moment of merger when two become one. This is followed by a rapid decay in sound, the ring down as the new, larger black hole settles into a stable, quiet sphere, vibrating like a struck bell before fading into silence. This auditory signature is far more than just a neat trick. It's a powerful analytical tool. Just as a musician can identify an instrument by its sound, astrophysicists can analyze this chirp to determine the properties of the black holes that created it. The specific frequencies involved, the rate at which the pitch increases, and the duration of the ring down all contain encoded information. By carefully studying the shape and sound of the waveform, scientists can calculate the masses of the two original black holes and the mass of the final merged object. They can even infer the black hole's spins and their orientations. This is a form of astronomy that is completely independent of light. We are no longer relying on photons to tell us a story. We are using the vibrations of spacetime itself. It allows us to observe events that are completely dark, like the collision of two black holes in a void, far from any gas or dust that could glow and create an electromagnetic signal. This chirp is their only cry, a fleeting announcement of a cosmic marriage that reshapes the geometry of the universe on a scale we are only just beginning to perceive. But what if the most extreme objects in the cosmos weren't confined to the depths of space? What if we could create one right here on Earth? This leads us to a concept that sounds like it's ripped from a science fiction thriller, but is grounded in serious theoretical physics. The possibility of creating miniature black holes in a laboratory. Specifically, the world's most powerful particle accelerator, the Large Hadron Collider, or LHC, has been considered a potential birthplace for these tiny, fleeting specks of immense density. The idea stems from Einstein's famous equation, E equals mc squared, which tells us that energy and mass are two sides of the same coin. The LHC works by accelerating protons to velocities incredibly close to the speed of light and then smashing them together head-on. In that brief, cataclysmic moment of collision, the kinetic energy of the protons is concentrated into an unimaginably small point. According to the principles of general relativity, if you can pack enough energy into a sufficiently tiny volume of space, you will create a black hole. The energy required to make a black hole with the mass of, say, a mountain is far beyond our capabilities. However, if certain theoretical models are correct, the energy needed could be much, much lower. This is where the fascinating idea of extra dimensions enters the picture. Our everyday experience tells us the universe has 3 spatial dimensions plus time. But theories like string theory propose that there could be many more dimensions, perhaps 7 or more, curled up into sizes so small we never perceive them. If these extra dimensions exist, gravity, which seems relatively weak in our 3-dimensional world, could actually be a much stronger force that is diluted as it spreads out through these hidden dimensions. In such a scenario, the energy threshold required to warp spacetime enough to create a microscopic black hole could be within the reach of the LHC. The creation of such an object would be far more than a novelty. It would be one of the most profound discoveries in the history of science, offering the first direct experimental evidence for these extra dimensions and providing a crucial window into a theory of quantum gravity. Now, the moment this concept is mentioned, a very understandable question arises. Wouldn't that be incredibly dangerous? The image of a tiny black hole falling to the center of the Earth and devouring the planet from the inside out is a classic doomsday scenario. However, physicists have thoroughly investigated this possibility and concluded it is simply not a threat. The reason lies in the very phenomenon we discussed earlier, Hawking radiation. A microscopic black hole created in a particle collision would be incredibly small and incredibly hot. Stephen Hawking's work showed that such a black hole would lose mass through radiation at a tremendous rate. In fact, a black hole with the mass of a few protons would evaporate completely in a time span so short it's almost meaningless, something like 10 to the power of -27 seconds. It would vanish in a puff of particles and energy long before it could interact with, let alone consume, a single additional atom. It would be less stable than a soap bubble, popping into existence and then out again before any physical process could even begin. The safety of such experiments has been rigorously reviewed, and the consensus is clear. Any black hole we could create would be a fleeting, harmless spectacle. The true value of creating a micro-black hole would be for the priceless data it would provide. Observing its evaporation via Hawking radiation would allow us to study this quantum gravitational effect directly for the first time, testing Hawking's predictions with unprecedented precision. Analyzing the specific particles and energies emitted as it decayed would be like reading the fingerprint of the fundamental laws of the universe at the Planck scale. So, while the Large Hadron Collider has not yet detected any signs of microscopic black holes, the search itself pushes the boundaries of our knowledge. It represents a breathtaking endeavor, using a machine built by humanity to recreate, for a fraction of a moment, the most extreme conditions of the early universe, probing the very fabric of reality to see if it contains secrets far stranger and more wonderful than we ever imagined. This brings us to a possibility that truly stretches the limits of scientific imagination, a concept that has fueled countless science fiction stories but emerges directly from the cold, hard mathematics of Einstein's theory. The idea that black holes might, in theory, function as tunnels not just through space but through time itself. We've already seen how their immense gravity warps time, slowing its passage for an outside observer. But what if that warping could be twisted into a loop, creating a path that circles back on itself? This is the realm of closed time-like curves, or CTCs, and it's one of the most mind-bending consequences ever teased out of the equations of general relativity. To understand what a closed time-like curve is, we first need to break down the terms. In the language of relativity, your path through the universe is a world line through the four-dimensional fabric of spacetime. A time-like curve is simply a path that any object with mass can follow, where you're always moving forward through time at less than the speed of light. It's the normal trajectory of life. Now imagine if that path, instead of stretching inexorably toward the future, curved around in such a way that it connected back to a point in its own past. Your world line would form a loop. You would travel along this loop and eventually return to the very same event from which you started. This is a closed time-like curve, a theoretical pathway through space-time that could, in principle, allow for travel into your own past. So, where could such a fantastical path exist? The most commonly discussed theoretical setups involve not just a standard black hole, but specific, highly idealized solutions to Einstein's equations. One intriguing possibility revolves around a rapidly rotating black hole, described by the Kerr solution we discussed earlier. The mathematics suggest that deep within the structure of such a black hole, past the event horizon but before reaching the central singularity, there might be a region where the extreme twisting of spacetime could create these closed loops. Another, perhaps more famous, candidate is the stable, traversable wormhole. If such a thing could exist, a tunnel with two mouths connecting different points in spacetime, then by manipulating one of the mouths, perhaps by moving it at a significant fraction of the speed of light or placing it in an intense gravitational field, you could create a time difference between the two ends. One mouth could become the past entrance and the other the future exit, effectively turning the wormhole into a time machine. However, and this is a monumental however, moving from mathematical possibility to physical reality introduces a host of seemingly insurmountable problems. The first and most famous is the grandfather paradox. Imagine you used such a time machine to travel back to a time before your grandfather had children. What would happen if you were to prevent him from meeting your grandmother? If you succeed, then you would never be born, which means you could never have traveled back in time to interfere in the first place. This creates a logical contradiction, a loop of cause and effect that seems to violate a fundamental principle of the universe, that cause must always precede effect. Physics abhors such paradoxes, and many physicists take this as a strong indication that nature must have a law, perhaps yet undiscovered, that prevents closed time-like curves from forming in the real world. Some solutions to the paradox involve the concept of self-consistency, where any actions you take in the past were always a part of history, meaning you would inevitably fail to change anything in a way that creates a contradiction. Your attempt to alter the past might, through a convoluted series of events, be the very thing that ensures it happens exactly as it always did. Beyond the logical nightmares, the practical and energy requirements to create a stable time machine are almost certainly beyond any conceivable technology. As we touched on with wormholes, keeping the throat of a time tunnel open would likely require exotic matter with negative energy density, a substance we have no evidence for and no idea how to create or contain. The energies involved would be astronomical, on the scale of manipulating entire stars or more. Furthermore, the stability of these theoretical constructs is highly questionable. Many physicists believe that the moment you tried to create a closed time-like curve, quantum effects would conspire to destroy it. The vacuum fluctuations of empty space might amplify to infinite energy levels, creating a feedback loop that would vaporize the time machine before it could ever be used. This is often referred to as the chronology protection conjecture, an idea proposed by Stephen Hawking, which whimsically suggests that the laws of physics must have a built-in mechanism to prevent time travel, thereby making the world safe for historians. So, while the equations of general relativity leave a tantalizing door slightly ajar, the overwhelming consensus is that a series of physical safeguards, both known and unknown, slam it shut. The true value of exploring these ideas is not in building a time machine, but in using these extreme thought experiments to probe the absolute limits of our best theory of gravity, forcing us to ask deeper questions about the fundamental nature of causality and the structure of the universe we call home. But our journey into the violent dynamics of black holes doesn't end with their merger and the resulting gravitational wave chirp. That moment of union has a potential aftereffect, a cosmic recoil so powerful it can literally boot the resulting black hole right out of its galactic home. This phenomenon is known as a black hole recoil, or more dramatically, a black hole kick, and it occurs when the universe's most powerful explosions are not perfectly symmetrical. To understand this, imagine two figure skaters holding hands and spinning rapidly around a common center. If they were to let go at exactly the same moment and with exactly the same force, they would fly apart in opposite but perfectly balanced directions, their center of mass remaining stationary. Now imagine if one skater is much stronger than the other. When they let go, the release would be lopsided. The stronger skater would be pushed back with less force, while the weaker one would be flung away more violently. Their combined center of mass would itself move, recoiling from the point of separation. A black hole merger is an infinitely more violent version of this, but instead of skaters pushing off with their arms, the force comes from the torrent of gravitational waves blasting out into the universe. The key factor is asymmetry. If the two merging black holes have identical masses and perfectly aligned, equal spins, the gravitational waves will be emitted symmetrically in all directions. The final, single black hole will form right where you'd expect it, but if the black holes have different masses, or if their individual spins are misaligned or of different strengths, the emission of gravitational waves becomes dramatically lopsided. In the final frantic moments of the merger, more gravitational wave energy is shot out in one particular direction. To conserve momentum, the newly formed black hole must recoil in the opposite direction, just like a rocket recoils from the expulsion of its exhaust. The mathematics of general relativity predict that these kicks can reach staggering velocities, in some cases over 5,000 kilometers per second. That's enough to escape the gravitational pull of even the largest galaxies. Picture the aftermath of such an event. A supermassive black hole weighing millions of suns is suddenly sent careening through its host galaxy at a significant fraction of the speed of light. It would be a ghost ship, a gravitational titan stripped of its kingdom, voyaging through the immense voids between galaxies. Astronomers have, in fact, been hunting for these runaway black holes. The telltale sign would be a bright, active quasar, the black hole's accretion disk shining brilliantly, but located far from the dynamical center of any galaxy, out in the galactic suburbs or even in the empty intergalactic wilderness. While definitive proof of a high-velocity kick remains elusive, several strong candidates have been identified, quasars that appear offset from their host galaxies' cores by vast distances, suggesting they were given a mighty shove. This incredible process transforms our view of black holes from static anchors at the hearts of galaxies to dynamic objects that can be born, merge, and even be exiled, forever changing the structure of the cosmic landscape they leave behind. But for all their destructive power, black holes may also be cosmic creators, playing a vital role in forging the very elements that make up our world and even our own bodies. We often think of the universe's ingredients as being manufactured in the hearts of stars, and that's true for many of the lighter elements. But when it comes to the very heaviest, most precious metals, the gold in your jewelry, the platinum in a catalytic converter, the uranium in nuclear reactors, their origin story is far more violent and involves some of the most extreme events imaginable, events where black holes can be key players. To understand this cosmic alchemy, we need to look at a process known as the rapid neutron capture process, or the R process for short. This is how nature builds atoms heavier than iron. Inside an average star, fusion can only create elements up to iron because fusing anything heavier actually consumes energy instead of releasing it. So, to go beyond iron, you need a different method, adding neutrons to existing atomic nuclei. The rapid part is crucial. In this environment, neutrons are bombarding seed nuclei so quickly that the nucleus doesn't have time to undergo radioactive decay before even more neutrons are stuck on. This builds up an extremely neutron-rich, unstable nucleus that then settles down into a stable, heavy element through a series of decays. The challenge is creating the right conditions for this, an incredibly dense, hot, and neutron-rich environment where this frantic assembly line can operate. For a long time, scientists believed the primary cosmic forge for these heavy elements was the supernova explosion that marks the death of a massive star. And while supernovae do contribute, many models suggest they might not be neutron-rich enough or might not produce the heaviest elements in the quantities we observe in the universe. The search for a more powerful and efficient R-process site led to an even more cataclysmic event, the merger of two neutron stars. When these ultra-dense stellar corpses spiral together and collide, they spray out a cloud of neutron-rich material. In this hot, expanding debris, the conditions are perfect for the R-process to run wild, rapidly creating a whole spectrum of heavy elements. The evidence for this became spectacularly clear in 2017 when the LIGO and Virgo observatories detected gravitational waves from a neutron star merger. Following up with telescopes, astronomers saw the aftermath, a glow called a kilonova whose light signature contained clear evidence that vast amounts of gold and platinum, perhaps hundreds of Earth masses worth, were being synthesized right before our eyes. This is where black holes re-enter the story in a fascinating way. While neutron-star mergers are incredibly efficient, there's another theoretical scenario that might be just as important, or perhaps even more so: the merger of a neutron star with a black hole. Imagine this cosmic dance. A neutron star, a city-sized object more massive than our Sun, is locked in orbit with a stellar mass black hole. As they lose energy to gravitational waves, they spiral inward. If the black hole is large enough or has a certain spin, it may not gently rip the neutron star apart from a distance. Instead, it could swallow it whole with little debris left over. But if the conditions are just right, if the black hole is smaller or spinning rapidly, the tidal forces as they close in could shred the neutron star before it crosses the event horizon. This would tear the neutron star apart into a magnificent, swirling torus of ultra-dense, neutron-rich material around the black hole. This debris disk would be a crucible of unimaginable violence, even more energetic than the debris from two neutron stars colliding. The intense heat and density, powered by the gravitational energy of the infall and the magnetic fields of the black hole, would create a perfect environment for the R-process to operate at an extreme level, potentially producing a staggering abundance of the heaviest elements. The significance of this is profound. Every time you look at a gold ring or consider the rare elements in our technology, you might be looking at the ashes of a cataclysm that occurred billions of years ago, a cataclysm possibly triggered by the gravitational embrace of a black hole. These events seed the gas clouds that will eventually form new stars and planets. Without them, the periodic table would be a much shorter list, and planets like Earth might lack the diverse chemical makeup necessary for complex geology and perhaps even for life itself. So, in a beautiful and terrifying symmetry, the same objects that represent the ultimate end of matter are also instrumental in creating the richness and diversity of the elements that form the building blocks of everything we know. But if we project our gaze forward, past the vibrant lives of stars and the dynamic collisions of galaxies, we arrive at a future so distant it makes the age of the universe so far seem like the blink of an eye. This is the fate that awaits the cosmos, a chapter known as the black hole era, a time when the universe transforms from a brilliant fireworks display into a silent, dark, and profoundly cold expanse. To understand this era, we must first witness the end of everything we consider familiar. Over the next tens of trillions of years, the fuel for star formation will finally run out. The last stars will flicker and die, their corpses cooling into black dwarfs, neutron stars, and stellar mass black holes. Galaxies, no longer held together by the gravity of their stars, will slowly evaporate, their stellar remnants flung into the intergalactic void by chance gravitational encounters. The universe will become a vast, ever-expanding sea of darkness, punctuated only by the faint, cold embers of dead stars. In this profound and endless night, the only significant sources of gravity, the only true landmarks, will be black holes. They will inherit the universe. The stellar mass black holes formed from dead stars will wander the emptiness, and the supermassive black holes that once anchored galaxies will sit in the profound isolation of what were once galactic centers. For an almost unimaginable duration, these black holes will be the kings of a frozen realm. But even their reign is not eternal, thanks to the process we explored earlier, Hawking radiation. In the current, energy-rich universe, a black hole like the one in Cygnus X-1 is gaining more mass from the cosmic microwave background radiation than it is losing through Hawking radiation. But as the universe continues to expand and cool, that background radiation will fade to almost nothing, becoming colder than the black holes themselves. At that point, the slow, relentless leak will begin in earnest. The black hole era will be characterized by this excruciatingly slow evaporation. It will not be a time of dramatic events, but of imperceptible decay. The universe will be pitch black, its temperature hovering just above absolute zero. The only light, the only energy, will be the faint, cold glow of Hawking radiation emanating from the surfaces of these black holes. For trillions upon trillions of years, this will be the dominant form of energy release in the entire cosmos. A stellar mass black hole might take 10 to the power of 67 years to evaporate, a 1 followed by 67 zeros. A supermassive black hole like Sagittarius A star could take 10 to the power of 100 years. These timescales are so vast they have no connection to human experience. They are numbers that describe the fundamental ticking of the cosmic clock. As a black hole nears the end of its life, a fascinating transformation occurs. Remember, the rate of Hawking radiation increases as the black hole loses mass. The smaller it gets, the hotter it becomes, and the faster it evaporates. In the final second of its existence, a black hole with the mass of a small mountain would release the energy of 1,000,000 1-megaton hydrogen bombs in a tremendous flash of light and particles. Across the dark universe, these tiny, brilliant explosions would pop like firecrackers in an infinite night, each one signaling the final death of a gravitational titan. One by one, over epochs that defy comprehension, every black hole will vanish. First the small stellar mass ones, and eventually, after time spans that are truly meaningless to contemplate, the last supermassive black hole will detonate. When that final flash fades, the universe will enter its last conceivable phase, the dark era. With no black holes, no stars, and no sources of energy, the cosmos will become a perfectly uniform, ultra-thin soup of subatomic particles and radiation, stretched across an infinite and ever-cooling void, a quiet and permanent conclusion to the story of everything. This incredible journey through the life and death of black holes, from their explosive births to their slow evaporation across eons, brings us to a final, profound realization. The study of these cosmic extremes is not just about understanding the far future or distant corners of space. It is, remarkably, a journey back in time to the very beginning of everything. The ultimate value of peering into the abyss is that it gives us a unique and powerful lens through which to view the origin of our entire universe, the Big Bang. To grasp this incredible connection, we need to return to the most baffling feature of a black hole, the singularity. This is the point of infinite density at its heart, where the mass of entire stars is crushed into a volume of zero size. It is a place where the reliable laws of physics, the equations of general relativity that work so perfectly everywhere else, simply break down. The mathematics spew out infinities, a clear signal that our current understanding is incomplete, that we are missing a deeper theory. Now consider the Big Bang. The prevailing cosmological model tells us that our universe began not as a fiery explosion in space, but as a rapid expansion of space itself from an initial state. And what was that state? A point of unimaginable temperature, energy, and density. In fact, if we run the cosmic clock all the way back to time zero, the equation suggested, too, was a singularity, a moment when the entire cosmos was contained in a point of infinite density. The Big Bang, in its very first instant, was a universal singularity. This presents a stunning parallel. A black hole singularity represents a boundary in space beyond which our physics fails. The Big Bang singularity represents a boundary in time, a beginning point where our physics also fails. Both are realms where the classical smoothness of general relativity must somehow merge with the fuzzy, quantum nature of the subatomic world. This is the quest for a theory of quantum gravity, and black holes are the only natural laboratories we have to test ideas about it. We can never travel back to the first moment of the Big Bang to observe it directly, but we can observe black holes. By studying how gravity and quantum mechanics interact at the event horizon, and by developing theories about what happens at the central singularity, we are essentially running experiments on the same kind of physics that govern the universe's birth. When we probe the Hawking radiation leaking from a black hole, we are gathering clues about quantum fields in intensely curved spacetime, conditions that would have been universal in the first fleeting fractions of a second after the Big Bang. The implications of this are breathtaking. The same principles that might explain how information is preserved or lost in a black hole could resolve what happened at the dawn of time, potentially explaining how the universe emerged from a state of seeming chaos into the ordered, predictable cosmos we see today. The violent, high-energy collisions that create gravitational waves mimic the extreme energies of the early universe, allowing us to test our models of how matter and energy behave under such duress. In a very real sense, every black hole we study is a tiny, contained echo of the Big Bang itself. They are cosmic relics that allow us to explore the physics of creation from the safety of the present day. So, when we train our telescopes on the dark heart of a galaxy or listen for the chirp of a black hole merger, we are doing more than just cataloging exotic objects. We are reading the universe's own autobiography, deciphering the fundamental laws that brought everything from the largest galaxy to the smallest atom, and indeed us, into being. The black hole, this symbol of ultimate finality, has become one of our most important keys to understanding the beginning. And so, this incredible journey brings us full circle, from the theoretical predictions scribbled in the trenches of a world war to the stunning, direct images of shadows cast by gravity itself. We have ventured from the crushing death of massive stars to the supermassive titans that anchor entire galaxies, from the mind-bending warping of time to the faint, quantum whispers that hint at their ultimate evaporation. The picture that emerges is a universe away from the simple cosmic vacuum cleaner. Black holes are not passive holes in space, they are dynamic, powerful engines. They are the architects of galactic structure, their furious feedback governing the birth of stars and the very growth of the galaxies they call home. They are the ultimate paradoxes, challenging the very foundations of physics and forcing us to confront the uncomfortable edges of our knowledge, where relativity and quantum mechanics wage a silent war. And in doing so, they offer us the most profound clues to a deeper, unified theory of everything. They are not endpoints of destruction but potential wellsprings of creation, their violent mergers possibly forging the very gold and precious metals that make up our world. They are cosmic laboratories, time machines for thought experiments, and perhaps even echoes of the universe's own fiery birth in the Big Bang. The next time you find yourself under a clear, dark sky, take a moment to truly look up. Let your gaze drift toward the constellation Sagittarius, where the silent behemoth Sagittarius, a star, sleeps at the heart of our Milky Way. Or simply contemplate the profound darkness between the stars, knowing that it is teeming with countless gravitational ghosts, each a remnant of a stellar life lived long ago. That silent, starry tapestry is not a static painting. It is a dynamic, roaring arena where the most extreme events in creation are unfolding. It is a universe where space can be stretched like rubber, where time is a personal experience, and where the darkest objects can be anchors for the most brilliant light. Let this new understanding sink in. The universe is far stranger, more violent, and more wonderfully mysterious than we could have ever imagined. And our quest to understand it, to peer into the heart of darkness, is what continually reshapes our place within this vast, astonishing cosmos. We have covered 30 facts, but this is only the beginning of the story. The frontier of black hole science is expanding faster than ever. Which of these revelations resonated most deeply with you? Was it the sheer scale of a monster like Ton 618, or the personal, terrifying reality of spaghettification? Perhaps it was the philosophical shock of the information paradox, or the elegant beauty of hearing the universe's deepest notes through gravitational waves. Let the conversation continue down below. Share the fact that most expanded your mind in the comments. This is a journey we take together. If you're ready to keep exploring the wonders of the cosmos, from the birth of stars to the search for alien life, make sure to subscribe and hit the notification bell so you don't miss our next adventure into the mysteries of the universe. Thank you for joining us on this expedition to the edge of understanding. Keep looking up and never stop wondering.